Greetings to all the chemistry students. Welcome to the fifth part of our topic on Strand 2.1. In this session, we are going to be discussing about some of the very interesting types of covalent bonding. Now, in the earlier part, we discussed about how covalent bonding takes place when two nonmetals share electrons. In this part, we will be looking at a covalent bond where only one atom will be providing the electrons. Furthermore, we will also be studying how single and a double bond is going to form between nonmetals. So let's look at what dative bonding is and what sigma and pi bonding is. Dative bonding is also known as coordinate bond. It is a special kind of covalent bond where electrons are provided by only one atom. So this one atom, which is providing the electrons, has to have a lone pair of electrons on itself. Now, dative bonding doesn't only occur between atoms in a molecule. It can also take place between molecules, and this process is known as dimerization. So let's look at how dative bonding occurs between molecules. We are going to be studying two examples. Number one, dative bonding between aluminum trichloride molecules. So when we are looking at aluminum trichloride, this is an octet deficient molecule. The reason is, if you're looking at the configuration of aluminium in this particular electron dot diagram, you will notice that aluminium is having only 6 electrons around it instead of 8. So that makes aluminium an octet deficient atom. Having said that, it will try to ensure it gains extra 2 electrons to become stable, and that can only happen if it combines with another of the aluminum trichloride molecule. So the species which is willing to provide the 2 electrons to the aluminium will be the chlorine of another molecule. So the chlorine of the first molecule will be providing the lone pair of electrons to the aluminium of another molecule. And you can see in this process, aluminium is not sharing any of its electrons to the chlorine. Hence, the term dative bonding takes place. Likewise, the chlorine of another aluminum trichloride molecule will be sharing its electrons to the aluminum of the first one. And by doing that, both the molecules are going to be combined as one, as Al2Cl6. If you're looking at the structure of Al2Cl6, you can see that there are two arrows which are drawn here. These arrows indicate the formation of a dative bond. The direction of the arrow indicates the electrons provided by chlorine atom to aluminium. And you can see the structural formula as drawn here. The next example of dative bonding between molecules occurs between ammonia and boron trichloride. Boron trichloride, just like aluminium trichloride, is an octet deficient molecule where boron is in need of 2 extra electrons, and that 2 electrons it will be getting from ammonia, simply because the nitrogen in the ammonia is carrying a lone pair of electrons. So these lone pair of electrons on the nitrogen atom in ammonia can easily be shared to the boron atom of boron trichloride, and as a result, these two molecules will be now combined as one through the formation of a dative bonding. And since it is a dative bonding, notice the arrow that is being drawn between nitrogen and boron. The arrow indicates dative bonding, and the direction of the arrow indicates that the nitrogen is the one providing the electrons to the boron atom. Now we are going to be looking at how dative bonding occurs in ions. There are two types of ions which will involve dative bonding: cations and anions. Both cations and anions will have different set of rules when we are drawing the dative bonding in them. So when we're looking at cations, which are positive ions, we have to keep in mind a certain trick. In cations at a certain level, you will be tested on ammonium ion and hydronium ion. Therefore, it is advisable that when we are drawing the Lewis structure of these cations, we draw the parent molecule first and then we pair that up with a H plus. So a cation such as ammonium ion, it is formed when ammonia is combining with a H plus. H plus or a proton is carrying an empty orbital. It doesn't have any electrons. Therefore, it is in need of two electrons to make it stable. So the first thing we will be doing is to draw the parent molecule, which is ammonia. The Lewis structure of ammonia is a trigonal pyramidal shape, where you can see that the nitrogen is carrying a lone pair of electrons. Now, because there is a H plus which is coming and attaching itself to the ammonia molecule, that H plus is an empty orbital. It needs two electrons, and that two electron it can gain from the nitrogen. So it will simply come with its empty orbital and attach to the nitrogen. Remember, the hydrogen that has attached here is not sharing any of its electron. Instead, it is a nitrogen that is sharing its electron to the hydrogen. Therefore, a dative bonding has been formed between the nitrogen and the new hydrogen that has come in. Now, because it is an ion, we must include square braces. Whenever we draw a Lewis structure of an ion, it is important that we draw square braces and put the charge on the top right-hand corner. So this is how we draw the Lewis structure of ammonium ion. We can also draw the structural formula of ammonium ion using the similar method, where instead of the bond, the electron and dot, we can simply use a bond. Keeping in mind that since there is a dative bonding between the nitrogen and the hydrogen, we must ensure that we draw an arrow. The arrow will indicate the direction in which the electrons are being shared. So here, nitrogen is the one sharing the electrons with the hydrogen. That is why the arrow is drawn from nitrogen to hydrogen. Next, let's see how we are going to draw the Lewis structure of hydronium ion. Once again, when we are drawing the Lewis structure of a cation, keep in mind we are drawing the Lewis structure of the parent molecule first and then attaching the parent molecule with the H plus. The H plus is a proton which doesn't have any electrons, which is why it is needing two extra electrons to make it stable. So the parent molecule in hydronium ion is water, which will combine with the H plus. So let's see how the water molecule can be drawn. So this is how the water molecule looks like. A band or a V shape. The oxygen in the water is carrying two lone pair of electrons. One of the lone pair of electron can be given or can be shared with the H plus. So when that happens, the H plus that is coming in is going to attach itself to one of the lone pair of electron. The H plus is not sharing any of its electron. It is only the oxygen that is sharing the electrons to the hydrogen. Hence, a dative bonding is formed between the oxygen and the hydrogen. Now, because it's a cation, we must draw the square brace and put the charge on the top right-hand corner. When we draw the structural formula of this hydronium ion, this is how we draw it. And just like we did it for ammonium ion, because there is a dative bonding between the oxygen and the hydrogen, we must include an arrow. So this arrow is going to indicate the electrons being shared by the oxygen atom only and received by the hydrogen atom. So students, I hope that you have understood the trick into how you are going to draw the Lewis structure of a cation, namely anions, namely ammonium ion and hydronium ion. Now, when we are drawing the Lewis structure of an anion or a molecule, the first thing we must do is to note the electron configuration of the atoms and then focus on the valence electrons only. So example number 3, draw the Lewis structure of a nitrite ion, NO2 minus. Configuration of nitrogen is 2,5, while the configuration of oxygen is 2,6. Now you can see that I have written a very basic configuration here, which is okay because we are not going to be penalized by writing this configuration. This is just our working to work out the valence electron and work out the repulsion on the molecule or the ion. Okay, so the valence electron on nitrogen is 5, while the valence electron on oxygen is 6. So first thing we do is to position the atoms. One nitrogen surrounded by two oxygen atoms. Okay, now we are going to put the valence electron around the atoms. So nitrogen has 5 electrons. We will draw the 5 electrons around nitrogen in pairs. So that's 1, that's 2, that's 1 pair, that's 3, 4, and that's a fifth electron. Now because you can see here in this particular structure that this particular electron is unpaired. We cannot have an unpaired electron um, in a molecule or in an ion. If there is an unpaired electron, then it will create an unstable radical. So what will happen is the negative charge that is here on the nitrite ion, NO2 minus. So this negative charge will be given to this particular nitrogen. That negative charge means 1 electron, okay, an extra electron. So now nitrogen has a total of 6 electrons. How many electrons do you think it needs to become stable? It requires 2 extra electrons, and that 2 extra electrons can come from one of the 2 oxygen atoms. So one of the 2 oxygen atom will be providing 2 electrons to this nitrogen. And this is the oxygen that will be providing the electrons. You can choose either of these oxygens to provide the electron. It doesn't really matter. But I have chosen this oxygen here. So if this oxygen has provided 2 electrons already, how many lone pair of electrons will it have now? This oxygen, the valence electron had was 6, isn't it? So 6 electrons were there, out of which 2 already has been shared. The balance is 4. So we are going to draw the 4 electrons in pairs. So there we have it now. Now what will happen to this particular oxygen now? Nitrogen is already stable with 8 electrons. So that's 2, that's 4, that's 6, and that's 8. So nitrogen is already having 8. It doesn't need any extra electron. So this oxygen is not going to provide any electron to this nitrogen. Therefore, it will keep the 6 electron with itself. So where do you think the dative bonding has taken place? The dative bonding has taken place between this nitrogen and this oxygen, because here the nitrogen is providing the electron to the oxygen, not oxygen providing the electron to the nitrogen. So only one atom is providing the electrons, okay? So that's the dative bonding. And because it's an ion, we must draw the square braces and put the charge on the top right hand corner. The next thing that I want to highlight is when we have to draw a structural formula of nitrite ion. How are we going to do that? So it's very simple. We just have to work it out from the Lewis structure that we have drawn just now. So we have a nitrogen atom and there is a double bond. Okay, keep in mind that one bond is between one dot and cross, and there is a single bond between this nitrogen and the oxygen. So since we have a dative bonding between this nitrogen and oxygen, we must draw the arrow that will be pointing towards oxygen, indicating that nitrogen is the one providing the electron to the oxygen only and not oxygen providing any of its electron to the nitrogen. And then to wrap it up, we have the square braces. Okay, so very neatly with this ruler we have to draw the square braces and put the charge on the top right hand corner. And not forgetting the lone pair of electrons. So this is the Lewis structure and the structural formula of nitrite ion. The shape of this ion is a bent or a V shape because the lone pair of nitrogen is repelling the bond pairs. That repulsion is greater than the bond pair to the bond pair repulsion. Example number 4. Let's see how we draw the Lewis structure of nitrate ion now. NO3 minus. So just like earlier, we write the electron configuration and we just position our atoms. Okay, so we have put the 3 oxygen atoms randomly around the nitrogen. Next, we are going to put the valence electron around each atom, not the lone pair, the valence electron. The valence electron on nitrogen is 5. So let's put the 5 electron. That's 2, that's 4, and that's 5. So 5 electrons are there for nitrogen and it will get an extra electron from the negative charge. So now a total of 6 electrons, which means it needs only 2 electrons to become stable. And that 2 electrons, I have decided to use this oxygen here, which will provide the 2 electron to the nitrogen. So now a total of 2, 4, okay, let's count. So we have a total of 2 here, 4, 6 and 8. Nitrogen has 8 electrons around itself. It doesn't need any extra electron. So what will the other 2 oxygen atoms do? The other 2 oxygen atoms will keep their 6 electrons around it. That is where the dative bonding will happen. Okay, so now this oxygen is left with 4 electrons, and that 4 electrons can be drawn around it, while the other oxygen atoms will keep their 6 electrons. Okay, so we're just going to draw the 6 electrons around this oxygen now, and there we have it. All the 3 atoms are stable. Then we put the square braces and the charge on the top right hand corner. Okay, furthermore, let's try to draw the structural formula. The nitrogen atom, notice that it doesn't have a lone pair of electron. Okay, so we have a dative bonding between this nitrogen and the oxygen that is on top here, and a dative bonding between the nitrogen and the oxygen, which is over here, and then over here we have a double bond. Okay, so this is a double bond, and not forgetting the final stage will be our square braces, and then putting the charge on the top right hand corner. So this is the structural formula of nitrate ion. The repulsion here is between the bond pairs, maximum bond pair to the bond pair repulsion. Okay, so that's a trigonal planar shape. In example 3, let's draw the Lewis structure of sulfur dioxide molecule. It's a molecule, not an ion, but we are going to do the same thing. We are going to look at the configuration and focus on the valence electron only. So let's draw the sulfur and the 2 oxygen around it, and then put the valence electron around each atom. I choose the central atom first because it's far more easier to start it with that. So I'm going to put the 6 electron around sulfur. There we go. How many extra electrons does sulfur need now? Sulfur needs an extra 2 electrons to make it 8, isn't it? And that 2 electron can be provided by either of these oxygen atoms. So this time I'm going to choose this oxygen here, which is going to provide the 2 electron to the sulfur. So altogether now sulfur is having 8 electrons. So how many electrons will remain for this particular oxygen now? Out of 6, it has already drawn shared 2. So it's left with 4, and that 4 I'm going to draw in pairs. And for the other oxygen, it's going to keep its 6 electron around itself. So this particular oxygen is keeping its electron and only getting electrons from the sulfur. So there is a dative bonding between the sulfur and the oxygen. So if I have to draw the structural formula of this particular molecule, it will be S. Okay, so this is where the dative bonding has happened. A dative bonding to this oxygen here, and there is a double bond between the oxygen and the sulfur, right? And then the lone pair on the sulfur atom. So that is a band or a V shape. The lone pair is pushing down the bond pairs, and the bond pairs repelling each other as well. Next, we have a sulfur trioxide molecule. So we're going to do the same thing here. Put the central atom. Let's surround it by the 3 oxygen atoms. And then we will be putting the valence electron around sulfur first. So 2, 4, 6. Okay. It requires extra 2 electrons, and this time I'm going to choose this oxygen. You can choose any of the oxygen which is going to provide the electron. It doesn't really matter. Okay. So I'm going to choose this oxygen here where the 2 electrons are provided by it to the sulfur. So sulfur now has 8 electrons. And this oxygen is now left with 4 electrons out of the 6. So we have the 2 pairs on this oxygen atom, whereas the other 2 oxygen atoms will keep their 6 electrons around it and only going to get the share electrons from the sulfur. So there we have it. This is the Lewis structure of sulfur trioxide molecule. And when we draw the structural formula, this is how it's going to be looking like. We have a sulfur atom. There is a double bond between the sulfur and the oxygen going up. Once again, remember one dot and a cross represents one bond. So there is a total of 2 bonds here, double bond. And there is a dative bond where sulfur is providing the electrons to the oxygen and not oxygen providing any of its electron. So there are 2 dative bondings formed between the sulfur and the oxygen. So this is the structural formula of sulfur trioxide molecule. There is a maximum repulsion of the bond pairs, so the shape is trigonal planar. So all this while we have been talking about electrons being shared between elements. This sharing of electron that occurs in non-metals in order to form the covalent bond actually happens due to the formation of a sigma or a pi bond. So keeping in mind what we have learned in our first part of atomic structure and bonding, the electrons are located in special parts of the shell which is called orbitals. These are regions in space where we are going to find the electrons. So when the electrons are being shared between the elements, it is the orbitals that will be overlapping between them. Okay, and this overlapping of orbitals is going to create an electron density, an electron cloud density. This electron cloud density will decide the number of bonds that can form. So when we are looking at sigma and pi bonds, they are covalent bonds still, but they are formed when there is an overlap of the atomic orbitals. So let's see how sigma and pi bonds formed. First, we are going to be looking at the formation of a sigma bond. Sigma bonds are single bonds. So all the bonds that are formed in a molecule which are single, they are sigma bonds. Okay, so let's see some of the ways in which a sigma or a single bond can be formed between the atoms. So we're going to be looking at one example. First of all, the first method by which a sigma bond is formed is when there are two s orbitals overlapping each other. Okay, let's say for example in hydrogen molecule. In a hydrogen molecule, there are two hydrogen atoms which are sharing the electrons. The configuration of the hydrogen is 1s1. That means the electrons that have to be shared will be residing in the s orbital of the hydrogen. So when this hydrogen shares one electron between the other hydrogen or with the other hydrogen, it is the s orbitals of these two hydrogens that is going to overlap. So this is how we can represent the overlap diagram as. Okay, so this is the s orbital which is spherical in shape of hydrogen 1, and this is the s orbital of hydrogen 2. So both these two hydrogens are coming together, and as a result they are overlapping the orbital. Now when this orbital is overlapping, notice that this area here which is intersecting is where the two electrons from each of the hydrogen is going to be concentrated. So we say that this is an area of electron cloud density. Now because one of such region has been formed here, it is going to result in a single bond. So one electron cloud density will result in a single bond. Okay, so we can say that hydrogen of one and the hydrogen of the other, when the two s orbitals overlap, there is one region of electron cloud density which is going to result in the formation of one bond, which is a sigma bond. So that is how single bonds are formed between the hydrogen atoms. Okay, then we have the second way in which a sigma bond is formed, when an s orbital and a p orbital is going to overlap. Let's look at the example HF. Hydrogen's configuration is 1s1. That means the electron that has to be shared by the hydrogen resides in the s orbital, while for fluorine, the electron that will be shared in the fluorine will reside in the p orbital. Recall that p orbitals can have three orientations: on the x-axis, y-axis, or even on the z-axis. So only on one of the axes is going to overlap here. Okay, so this is what happens now. The s orbital of the hydrogen, which is this one here, spherical orbital of hydrogen, and the p orbital of the fluorine. Okay, so the p orbital of fluorine is going to have their 5 electrons, isn't it? But these 5 electrons simply means that one of the orbital is unpaired. So this orbital is unpaired. It contains only one electron. It requires another electron. Okay, so when these two orbitals overlap, you can see that again there is a region of electron cloud density. So there is one region of electron cloud density formed here. And when there is one region of electron cloud density, there will be a formation of one bond between hydrogen and fluorine. So this is how single bonds form between s orbitals, between s and p orbitals. And lastly, the other way in which a sigma bond can form is when p orbitals overlap each other. Example, fluorine. In a fluorine molecule, the electrons that have to be shared in a fluorine is residing in the p orbital. So when that happens, the two p orbitals come along the x-axis. Okay, so when these two p orbitals come along the x-axis, we say that is known as the end-to-end overlap. So end-to-end overlap will again result in a formation of one region of cloud density. So this one region of electron cloud density will result in the formation of a single bond. Okay, so these are the three ways in which a sigma bond is formed. Next, let's see how a pi bond is formed between the two atoms. In a pi bond, there will always be a sideways overlap of the two p orbitals. And in order to form a pi bond, we must always draw a sigma bond first. So whenever bonds are drawn, sigma bonds are drawn first, followed by the pi bonds. Okay, so let's see how we are going to form a pi bond. Pi bond will also allow atoms to have a double bond or even a triple bond. So at a certain level, we are not going to be involved into the formation of triple bonds, but we will follow the method of how pi bonds result in the formation of a double bond only. And one suitable example is oxygen molecule. The configuration of oxygen is 1s2, 2s2, and 2p4. That means this oxygen requires two electrons to become stable. So there are two orbitals in the p orbital which are unpaired. Okay, so when the two electrons need to be shared between the two oxygen atoms, this is how the orbitals will come, okay, in overlap. So this one oxygen will bring its two electrons and the other oxygen will also bring its two electrons. Recall from the first session that I have done with you people, where I told you number of electrons required will be equal to the number of electrons an atom is going to share. So because oxygen requires two extra electrons to make it stable, it will share two electrons, okay, with each other. So that is why the two electrons are going to be shared. So when these two orbitals overlap sideways, it is going to form two electron cloud density region. So that's one electron cloud density region and that's another electron cloud density region. And when that happens, then there will be a formation of a double bond between the two oxygen atoms. So this is the reason why a double bond forms between oxygen molecule. So the important things we have to realize here is how sigma bonds and pi bonds are formed using relevant examples. And then the second part is you must be able to determine the number of sigma bond and a pi bond in a given molecule. Now all single bonds are sigma bonds. Okay. In a double bond, there will always be one sigma and one pi bond. While in a triple bond, there will always be one sigma and two pi bonds. Let's look at two examples. Example 1. How many sigma and pi bonds are there in this particular molecule? So let's count. There's 1, 2, 3, 4, and fifth one. This fifth one is determined as a sigma bond because in a double bond, one of the bond will be sigma. So a total of 5 sigma bonds and 1 pi bond. Okay. So double bond has 1 sigma and 1 pi bond. Next example. So we have this particular molecule here. Let's see. So that's 1, 2, 3, 4, 5, because in a triple bond, one of the bond will be sigma. Remember that, okay? So that's the fifth one, and that's the sixth one. So a total of 6 sigma bonds. Now, because there's a triple bond has 2 pi bonds. So the pi bond total is 2. Okay, students, so now I hope that you have learned and understood a lot about dative bonding and sigma and pi bonding. Time for the quiz. So the question for today is, draw the Lewis structure of sulfate ion. You can pause the video and see if you're able to draw this one. Check your answers. Is this what you have here? Notice that there are 4 dative bonds drawn around the sulfur atom. Each of the 4 oxygen atoms is keeping their 6 electrons around it. Okay, so sulfur has 6 electrons. Valence electrons is 6, so 6 electrons are drawn around sulfur. Plus, the negative 2 charge means 2 extra electrons is provided to the sulfur. So altogether, sulfur is having 8 electrons. It doesn't need any extra electron, which is why the 4 oxygen atoms are keeping their electrons with it. The second question is, identify the number of sigma and pi bond in this particular molecule. So now let's see what your answer is. A total of 10 sigma bonds and 3 pi bonds. Well, students, I hope you have understood how we have obtained the answers. Until then, you take care. Keep on going over your notes. Keep on going over the videos. If you have any queries, please, you can write your comment in the comment section below. I will be meeting you in the next session where we are going to be discussing about intermolecular bondings. Take care. Bye.